This lesson is going to talk about a new kind of angle that are now called inscribed angles. We've got two objectives here. We've got to be able to find the measure of an inscribed angle, and then to be able to find the measure of an angle formed by a tangent and a chord. As I said with the previous lesson, really good idea. Take down notes on all these theorems. Try to make yourself like a synthesized or set of notes for, based on what you see in the picture of a circle, what do you do? Is it something that involves angles? Is it something that involves chords? Is it something that involves arcs? And have that little cheat sheet, if you will, next to you, and that'll help you guys make this a little bit easier. All right? The way that I always like to think of an inscribed angle is think about that central angle. So remember, a central angle means that the vertex is at the center. And one thing that we learned about a central angle is it's equal to its intercepted arc. Now, I want you to take that vertex off the center and try to stretch it all the way back to the other side of the circle. So let's say, for instance, we have this arc AB right here, but now the angle that gets formed, its vertex is back over here on the circle itself. This is what is called an inscribed angle. Okay? An angle inside of a circle whose vertex is on the circle and whose sides are both chords. Okay? Notice how the intercepted arc is still this arc out here, arc AB. Okay? So we have this theorem that's called the intercepted or inscribed angle theorem. And it says the measure of an inscribed angle is equal to half the measure of its intercepted arc. All right, so let's kind of copy this down. We've got arc AB here as an example. Let's put point C over there. And we have this inscribed angle ACB. I know that the measure of angle ACB is going to be half of its intercepted arc. Now, its intercepted arc is still arc AB. All right? So the measure of an inscribed angle, is equal to half of its intercepted arc. Okay? Now, based on that theorem, we have a couple of corollaries. Or remember, what a corollary is like more specific examples of a theorem in action. All right? And this first corollary to that theorem says, two inscribed angles that intercept the same arc must be congruent. Let's kind of take a look at what that's going to look like. Let's say that we have arc AB, and that's going to be my intercepted arc. Well, I could have this angle right here, angle ACB, but I could also have another angle that's going to contain the same arc here, and let's call this angle ADB. All right? And here's what I know. I know that if two inscribed angles intercept the same arc, then these have to be congruent. So because they are both intercepting this arc, I am able to conclude that angle ACB has to be congruent to angle BDA. And again, why? Because they intercept the exact same arc. Now, corollary 2 says that an angle inscribed in a semicircle is a right angle. Well, let's take a look at what that is going to look like here. So let's say that I've got a center right here. I know that a circle becomes a semicircle if that's a diameter. So now I'm going to sketch an angle here. Let's say that we have an angle whose endpoints are the endpoints of a diameter. So we'll call that AB, we'll call that C. Here's what I know. I know that the measure of angle ACB, ACB is going to be half of its intercepted arc, and its intercepted arc here is 180. that allows me to conclude that the measure of angle ACB has to be 90 degrees, or a right angle. Corollary 3 says the opposite angles of a quadrilateral inscribed in a circle are supplementary. All right. So let's say that I have a quadrilateral. If I have a quadrilateral, that means that I have 4 different vertices that are going to lie on the circle. Now, these 4 vertices could be in the shape of a rectangle. They could be in the shape of any quadrilateral. All right, I'm going to call these A, B, C, and D. All right, and here's what this tells me. And if you think about it, it does make sense. I know that angle A and angle C have to add up to 180 degrees. Now, if you look at angle A, its intercepted arc is BCD. If you look at angle C, its intercepted arc is DAB. Well, those 2 intercepted arcs make up the entire circle, so it makes sense that the inscribed angles should add up to half the measure of an entire circle. All right? We also can say that the measure of angle B plus the measure of angle D has to be 180 degrees. All right? Now, one of the things that I want to point out to you guys is I'm trying to do my best to describe all this on this video. Don't hesitate to go out there and look at other resources on the web. All right? Go to the internet, type in the exact corollary or the exact theorem or something, and you might have more animated visions or views or videos for you to look at to help you understand this stuff. All right, so let's look at some problems here. In this first example, I notice right away that that is an inscribed angle. I know that an inscribed angle, A, is equal to half its intercepted arc, and in this case, its intercepted arc is 116. I can very simply conclude that angle A must be 58 degrees. Take a look at this second example. I have to be able to find A and B. Well, the first thing I got to do is be able to find A. I know that A can be found by taking 360 all the way around the circle minus 142, which is what 82 and 60 would add up to. And if I do that arithmetic, 360 minus 142, I know that A is going to be equal to 218 degrees. Because I know that A is 218 degrees, I know that angle B will be half of that intercepted arc. And if you take half of 218, you get 109 degrees. All right, in this next problem, they want me to find 3 different angles. Well, let's see. There's a few different approaches. I'm going to do what comes first, or what I see first. I see that A is an inscribed angle, and its intercepted arc is 108. So I can automatically deduce that angle A must be 54 degrees. All right. I go to angle B. I notice that it's an inscribed angle because its vertex is on the circle. So I'm able to deduce that B is equal to half its intercepted arc, which is 60, or B is 30 degrees. Now, the problem is, how do you find C? Well, we haven't talked about when the vertex is just kind of an angle is kind of floating around in the middle. However, I do know that if that angle is C, this angle has to be C as well, because vertical angles must be congruent. And if that angle is C, I know that angles A, B, and C altogether make up a triangle. So C can be found by taking 180, the measure of the angles of a triangle, minus A plus B, which would be 84 degrees. And I could conclude that C must be 96 degrees. All right, let's take a look at this next one. They want us to find A, B, C, and D. Well, I'm going to find A first. All right. I know that A is part of the arc for the angle that is 100, the inscribed angle that is 100. So I know that if the inscribed angle is 100, its arc has to be 200, but 99 of it is already represented, which tells me that angle A has to be 101 degrees. Now I'm going to go ahead and put that 101 where the A is as well. All right. So what about arc B? I'm not seeing anything for arc B yet, so I'm going to come back to that. Or, no, I don't see it yet. Maybe you do, and that's great. I don't see it. I'm going to come back to it. I'm going to find C next. All right? And here's why I'm going to find C next. I recognize that this was a quadrilateral inscribed in a circle. And if the quadrilateral is inside or inscribed in the circle, then I know that opposite angles must be supplementary. So I know that C has to be 180 minus 96, or C would be equal to 84 degrees. And I also know D, its opposite angle is 100, so 180 minus 100, angle D would also be 80 degrees. All right? So now with all that given information, let me see what I can deduce here. Well, I know that if this angle is 96 degrees, then its arc is 192. But 99 of it is already taken care of. So if I take, and I'm just going to double check myself here, 192 minus 99, I know that, come on, skip over here. There we go. Sorry, my calculator keeps getting stuck. I know that this arc right here has to be 93 degrees. And I got that by subtracting here. All right. We have concluded that angle D had to be 80 degrees. So that means it has to have an intercepted arc of 160, in which 93 of it is already taken care of. So that's going to give me that arc B is going to be 67 degrees. Okay? Might have been an easier way to do it. That was kind of what jumped out at me. If you guys saw something different, that's great. All right? Go to the next theorem here. The next example here. The next example. Oh, this one's pretty easy. I know that both X and Y are inscribed angles. I know that they share the intercepted arc, which means they have to be congruent. I know that X is going to be equal to half of 72, which means that X would be 36. And if X is 36, I'm able to conclude by that corollary that Y has to be 36 as well. All right, let's take a look at this theorem, or this example here. I noticed that line going through the middle there is a diameter, which means that splits the circle into two semicircles. So if I take 180 degrees and I subtract 95 from that, that'll give me arc A, 180 minus 95, or that arc A is 85 degrees. Okay? I know that angle B is an inscribed angle, and I know that its measurement is going to be half of its intercepted arc, which would be 95 degrees. Okay? Half of 95 degrees, let's double check it, but 95 divided by 2, I get 47.5. That's okay. We get a decimal. That's all right. 47.5 degrees. And then angle C, I know that its intercepted arc is a semicircle. So then I can say that C is half of 180, or that C would be 90 degrees. Okay? All right. For this next picture, let's see. The easiest way to do this, how do I find P and Q? I recognize that it's a quadrilateral inside. So opposite angles have to be supplementary. I know that P is 180 minus 90, or P is 90 degrees. I know that Q is 180 minus 58, or Q is 122 degrees. Sometimes they're that easy. All right, so let's take a look at this next theorem. I know there's a lot in this lesson, guys. There is a lot. All right, we got to know how to do it all and make sure we organize our thinking. It says the measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. We're really not learning anything new here. It's just we're bringing in a new type of segment within a circle. So if I have a tangent right here, all right, and this tangent creates an angle at the point of tangency, and that angle is a chord. All right, so let's call this A, B, C. All right, I know that the measure of angle A, B, C is going to be half its intercepted arc. Now, I'm going to put another point D right here, just so we know that the arc that we're talking about is arc BDC. This is exactly the same as the inscribed angle theorem. All right, it's just our inscribed angle looks a little bit different. So a couple more examples to make sure that we got this down. This one right here, how am I going to find angle W? Well, angle W is made up by a tangent and a chord meeting at the point of tangency right there, which tells me that W is equal to half its intercepted arc. And half of 246 would be 123 degrees. Take a look at this picture. All right, and I think that's it. Yeah, finally. All right. X is this angle inside of here, all right? In order to find X, we want to first, the smart way to do this is go ahead and find Y first. I know that Y is 360 minus 230, or Y is 130 degrees. I know that because 360 is all the way around the circle. So the arc Y is 130 degrees. If arc Y is 130, then angle X is an inscribed angle, which means its measure is half of its intercepted arc. In this case, 130, or X would be 65 degrees. All right, I hope this all helps. Again, guys, it is imperative with this stuff that you are taking good notes so you have something to look at when you're trying to do these problems. All right, good luck, and let me know how I might be able to help.